All right, so we're going to a brief overview of chemistry here. Now, disclaimer to start with, by no means should this substitute for any sort of chemistry class. A lot of this I absolutely don't care about. We're going to hit the high points of where it's relevant to what we're going to be talking about later and nothing else. I'm going to blow through a lot of this, and that's your cue to ignore, basically. It's background information. It's going to come up like in terms of big picture stuff, but by no means am I going to be testing you over that. In fact, I don't remember actually putting any specific chemistry questions on the exam. Now, that being said, that is not your cue to stop listening right now, because some of this comes up later, because I'm going to assume you know this. For those of you that have already had a chemistry class, that probably is your cue to stop now. If you've already had chemistry and you're freaking confident in chemistry, we should be pretty good, especially if you've got any organic chemistry knowledge. We're fine. But if not, this will catch you up with everyone so that we're all on the same page and you have at least that rudimentary knowledge of the organic chemistry that I need you to know as we go through. All right, so let's continue. Matter, anything that's mass occupies space, we're not going to talk about this. Energy, capacity to do work, everything that's alive is composed of matter and requires energy. All right, energy comes in different forms. We'll be talking about things like chemical energy and electrical energy. We don't really have anything to talk about with radiation or electromagnetic energy. I can't think where that's going to come up. In terms of our physiology, energy gets converted from one form to another. We lose part of this as heat. Everything that's going to happen in your body releases heat. We're just this big sum of chemical reactions. Everything that's going to happen is going to involve some sort of chemical reaction or the movement of charged particles around. More on this later. So elements, this does come up because you do need to kind of know some of these elements. Elements can't be broken down by ordinary chemical means, right? They're all different. They come on this big periodic table, looks like this. Here's the giant secret of chemistry. No one cares. How many of these are important? You're going to be honest? Like 24. 24 of them are relevant. Crap, all the clear numbered, like lettered ones here, those are fake. You'll see that little, there. They're synthetic. I mean, what the hell's that? It's got 3 U's on it. That's not a real word. Really? It's the same unium? What the hell's that? So these, like, seriously, Einsteinium? I'm supposed to think that's real? Yeah. Ignore. Which ones are important? Stuff that you're made out of, right? Those are inert. So stuff you're made out of, which ones do we care about? Sodium, potassium, calcium, carbon, oxygen. That's 5. Where's the 6th one on here? We need chloride, iron. Okay, I've got a chart of this, and I'm getting off track here, and I apologize for that. But hydrogen, there's my other one. Yeah, there's not a lot of these. You've got some of these trace minerals in here, like those guys. But yeah, these guys that are incorporated. But for the most part, we care about 24 elements. And if we're going to be completely honest, we care about 12. 6 elements make up nearly all of you. 98.7% of you. All right, so 6 elements, nearly all of you, right? Oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus. That's 98.7% of you. Now, just as a side note, oxygen, carbon, hydrogen, nitrogen, calcium, phosphorus. The rest of it is pretty much the sulfur, potassium, sodium, chlorine, magnesium, and iron. Sulfur, potassium, sodium, chlorine, magnesium, iron. The last 12 elements that are even remotely relevant are trace elements. These are less than 0.01% of you. But that's not to say they're not essential. Things like iodine and zinc are essential for your everyday metabolism. Zinc's important in the liver, and iodine's necessary to make thyroid hormone. Copper is involved in the electron transport chain. There's lots and lots of purposes for these to be in your body, but in really, really tiny amounts, right? You don't have like a cobalt deficiency where you really use some cobalt in your diet. It's found in such a small amount, you're going to get that. So some of these we'll talk about, iodine especially, in another semester. So I'm less concerned with these. 24 elements in normal physiology. There are other elements that might be incorporated in these things like mercury and lead. You don't want that in. So we're not going to be talking about this. Obviously, right, this is, again, stuff you know. Atoms are made of protons, neutrons, and electrons, right? Neutrons, protons, electrons. Look, there's an atom. Rock on. Again, I'm not going to be asking you how many electrons are in the valence shell of helium. You're just not super concerned with it. All atoms, right? So you have neutrons and protons and electrons. So the atomic number for helium is 2. Sorry. That 2 is the number of protons in the nucleus. So like hydrogen, it's 1. There's only 1 proton in the nucleus. The neutrons here, the yellow ones, are variable. Here's hydrogen, helium, and lithium. So you'll notice like hydrogen's got 1 proton and no neutrons. Helium, right, there's 2 of each, and lithium, there's 3 protons and 4 neutrons. The thing is they're even variable within the same elements. An isotope is a variation of the elements that have different numbers of neutrons. So there are different isotopes of every element. Here's isotopes of hydrogen. Standard hydrogen is there. This is called deuterium. Now, the only reason that I'm mentioning this now is deuterium, which is sometimes written as that 2H there, or sometimes it's written with a D because there's nothing on the periodic table with a D, so sometimes it's written as D, is actually being used in some medications now. The thing with isotopes is that isotopes react the same way as the sort of standard average form of the element. So you can make water with deuterium. Just messed that up. Right? So that's water, but because it's got that neutron, it makes it a little heavier. So we call that heavy water. There's actually some medications that should be hitting the market soon that incorporate that heavy water in it because hypothetically, they're more reactive. They're more active in the body. Now, I don't know. I haven't read the research on this. I really don't know how much more effective that's going to be, tritium is a radioactive isotope, and all elements have at least one radioisotope or radioactive isotope. All right, so I'm not worried about radioactivity, so it's there. Most of the time, though, we're not dealing with just like pure substances. We deal with multiple things bonded together. A molecule when multiple atoms are bonded together. A compound when two or more atoms are bonded together. Most matter, especially in the body, is not, again, existing in a pure form. It's existing as a mixture. So we'll talk briefly about mixtures. A solution is when we dissolve something, in our case, in water. So the solvent is usually water, and the solut's what's dissolved in water. Concentration exists or is expressed as moles or sometimes milligrams per deciliter, parts per hundred, whatever. You're not going to have to calculate molarity or anything, so don't worry about that. A colloid is, think like Jello with like giant chunks of gross fruit in or whatever. A suspension is like blood. If you let blood sit, the heavy part will settle to the bottom. So there's like a colloid solution and then a suspension. All right. So in any of those mixtures, you don't have any actual chemical bonds. In a compound, we get chemical bonds. So compounds will react because of the electrons in what's called the valence shell. Now, without getting into just a grand amount of detail, atoms react in such a way to fulfill this thing called the octet rule. Some elements are in there, we don't care. All right, so 3 types of chemical bonds we do care about: ionic, covalent, and hydrogen. Ionic bonds are the easiest to understand. Ions carry a charge because they have the unequal number of protons and electrons. Here is sodium. All right, so sodium, the atomic number is 11, so it has 11 protons and 11 electrons. Now, 1, 2. The first inner shell holds 2 electrons, and then each successive little ring out here will hold 8. So 3, 4, 5, 6, 7, 8, 9, 10, 11. Now, that 11th electron is just hanging out there by itself. The octet rule tells us that atoms want to have 8 electrons in that outside shell. So sodium would really like to ditch that electron. If sodium electrons are negative, if sodium wants to ditch an electron, it loses a negative, and that means that as an ion, sodium is positive. So the reason that we even mention chemistry at all is that guy right there. One day, during a lecture, I was writing these chemical equations. And someone actually raised their hand. They're like, why do you keep writing nat? Stop, reverse. Sodium. That's the sodium ion. Sodium Na ion positive because it's lost that electron. Now, chlorine's got the opposite issue. It's got 7 on that outside ring, so it just as soon pick one up. And if chlorine picks one up, that makes it negative. There's our chloride ion. Well, now we have a positive ion that's called a cation. It's lost the electron, it's positive. We have an anion. It's gained an electron, it's negative. Opposites attract. So sodium and chloride in this case are going to attract, and we get an ionic bond. An ionic bond is the attraction of these oppositely charged ions to each other. We're not sharing electrons, they're not physically joined together. They're stuck together like a magnet. They're not very strong bonds. They tend to dissociate or dissolve in water. They also tend to form crystals. Now, here is an important point. Sodium, in its pure form, as a metal. Sodium element, it's a metal. It's dull gray. It's kind of soft. You can cut it with a butter knife. It is highly reactive. It wants to ditch that electron. You can put a sliver of sodium out and it will react with the water vapor in the air and catch on fire. You can drop it in water and it will explode in a fireball of awesomeness. Chlorine exists again as a gas. It's a green gas. It's toxic. It'll burn your lungs and kill you. But as ions, these two things come together and we get sodium chloride. That's table salt. Now, when we've done this, we've lost the original properties of what we started with. You're not going to break that apart and get a flammable metal and green toxic gas again. It's a new thing. When we make these compounds, we make something new. It doesn't have the same properties. Now, I mention this because quite often people misunderstand how chemistry works here. One of the better cases of this is several years ago, and I may have spelled this wrong because I don't have it sitting in front of me. There's an additive that used to be in vaccines, the thimerosal. And the anti-vaccine lobby use this as an example because thimerosal is a compound that contains mercury, and mercury is highly toxic. But much like sodium chloride here, it loses those properties. So it doesn't have, it's not mercury. There's thimerosal. So it's got a mercury atom in there. That doesn't mean that it's mercury. It's a preservative. But just because of fear, it was removed. If you were to inhale it or eat it in high amounts, it would be bad for you. But it's cleared from the body pretty quickly. From 1999 forward, we don't use it anymore. Just because it's got that in there. But in the same aspect, you might be concerned with, chlorine and sodium chloride, but right, it doesn't maintain those original properties. So moving on, there's salt, rock on. Stronger than ionic bonds are covalent bonds. Covalent bonds means we share electrons. So here, we're actually joined by those electrons that are holding these molecules together. It's not just this attraction like magnets. There's ammonia, it's sharing of electrons there. Organic molecules tend to be held together by covalent bonds. It's a double covalent bond in carbon dioxide. Sometimes what happens is that those electrons don't get shared equally. So in this case, carbon, carbon, right? We have a symmetrical thing going on here. But here with oxygen and hydrogen, there's a lot more electrons around this oxygen nucleus there are around hydrogen. I mean, there's just 2 around hydrogen. So there's a lot more around the oxygen. Electrons are negative. And so this side of the molecule is more negative. That little symbol right there means partial negative, partial positive. One side of the molecule is slightly more negative than the other side. That makes it a polar molecule. This gives us our last type of bonds, the hydrogen bonds. Hydrogen bonds are the attractions between polar molecules. It's a very weak attraction, but it's really important for your physiology because hydrogen bonds give water its unique properties. That partial positive and partial negative are weakly attracted to each other, and we get this matrix of water. It creates surface tension in water. It means that water is a liquid at a wide range of temperatures. Stuff dissolves in water. Things that are hydrophilic dissolve in water. Hydrophilic molecules are polar molecules, much like water. Hydrophobic molecules are non-polar or neutral. They won't dissolve in water. This is going to come up later when we talk about cells. Water can act as an acid and a base. It acts in all sorts of chemical reactions. We're not going to get into this. And water sticks to itself. Look, there's surface tension. Those little indentations you see there around this little stupid bug, that's the surface tension of water. Water is used as a coolant. I'm not into this yet either. Again, we're blowing through chemistry and hitting the high points. Chemical reactions, just in case. I'm not going to ask you to balance chemical reactions to work this out. I'm doing this right now so that when I write this stuff out, you don't try to figure out how I'm adding letters together. I wish I was kidding. So, chemical reactions. There's a synthesis reaction. There's a decomposition reaction. Now, there's some terms here for you. Anabolic. Anabolic is building. I apologize. They put the little button on the stylus right where you would normally hold a pen. So I keep hitting it accidentally. So there's an anabolic reaction, building stuff. There's a catabolic reaction. Catabolic is breaking. Exchange reactions, right? We're rearranging stuff. There's chemical reactions will either release energy. Catabolic reactions release energy. Anabolic reactions will use energy, not use energy, but they contain more energy than you started with. It takes energy to make chemical bonds. All chemical reactions are reversible in chemistry, but in your physiology, most of them are not. It would just take too much energy to go back that other way. Quite often, the products are removed very quickly. Digestion, for instance, you break stuff down in the molecules, and those molecules are gone. Like they're in the bloodstream, they're out. You can't put it back together in that case. So most of our biological reactions, for all our purposes, are not going to be reversible. We'll talk about exceptions. Chemical reactions happen faster when it's hotter, when the particles are smaller, when there's more stuff. A catalyst makes this happen faster. An enzyme is a biological catalyst. Enzymes are proteins that act as biological catalysts. They speed up reaction. This is essential to how everything works. Enzyme-driven metabolism. Because often reactions don't happen quickly enough for our physiology. Example, lactose. It's the carbohydrate in milk. Lactose in the process of digestion is going to be converted into, well, it's going to be broken down into a molecule of glucose and a molecule of galactose. By itself, you can't absorb lactose. It's too big. We got to break it down into these smaller little pieces. Now, to do that, we have an enzyme in the intestines, lactase, which makes that happen fast. You don't have that enzyme. You don't have this reaction. And that lactose ends up in the large intestine where trillions of bacteria digest it for you, and it's not going to be fun from that point forward. You're lactose intolerant. So that enzyme is essential to making that digestive process work. And there's infinity other examples of this. Salts like sodium chloride go apart in water. They're electrolytes. Acids and bases are electrolytes. I'm not going to get into this or pH. All right, so under 7, acid. Over 7, alkaline or base. Look, there's your blood. The pH in your tissues is important. pH in your blood between 7.35 and 7.45, essential to everything working. Your blood acts as a buffer. A buffer resists changes in pH. So it's difficult to make the pH of your blood change by adding stuff to it because it acts as a buffer. Again, we're blowing through this and hitting the high points. Inorganic stuff, waters, salts, acids, bases. Organic compounds, here's where we get important. Carbohydrates, fats, lipids, proteins, nucleic acids. Organic compounds have carbon in them, they're big. They get names with weird side groups on them, they have long names. Here's the thing with organic molecules. Look at this, sucrose, lactose, maltose. Here's a phospholipid. Here's 2 molecules to look at. Ethanol and ethyl ether. Ethanol. What is ethanol? Ethanol is grain alcohol. It's alcohol, like you want to drink that alcohol. Here's its molecular formula, C2H6O. Ethyl ether. Ethyl ether is starting fluid in an engine. It's super flammable too. It'll knock you out, but it's a gas. It's not the same in higher amounts. It's going to be more toxic. But they're drastically different because of the arrangement here. So often in organic chemistry, we write things out like this. CH3, CH2OH, CH3, O, CH3. And it gives you an idea of the structural formula, whereas this does not. Because in organic chemistry, the structure is the important part. So organic molecules, carbohydrates, lipids, proteins, and nucleic acids. Carbohydrates all have the same formula, roughly 1 to 2 to 1, CH2O. So C6H12O6, right? But again, the structural part's the important. For instance, these are all C6H12O6, glucose, galactose, fructose. They're monosaccharides. There's disaccharides, sucrose, lactose, maltose. Again, they all have the same formula, but they're drastically different molecules. Here's polysaccharides, starch, cellulose, glycogen. Glycogen's the only one of these made by animals. It's our storage molecule for glucose. We'll find it in the muscles and in the liver. What are carbohydrates? Do we burn them? There are some structural ones, but most of the time, when we talk about carbohydrates, we're talking about the use of carbohydrates as cellular fuel. Now, lipids are hydrophobic. Carbohydrates are hydrophilic. Carbohydrates are polar molecules. These are non-polar molecules because they're hydrophobic. Only soluble in other lipids. Let's look. Here's the fatty acid. Lots of carbons, lots of hydrogens. We have a carboxylic acid, a methyl group. These chains of acetyls in the middle. Now, if we take 1, 2, 3 fatty acids with a glycerol, we get a triglyceride. There's a triglyceride. That's what you think of as fat. You'll hear the term saturated fat, unsaturated fat. Saturated fats are animal fats. They're solids at room temperatures. There are no carbon bonds in those fatty acid chains. An unsaturated fat is a liquid at room temperature. There's some double bonds in there. So there's a saturated fatty acid. You see there's no double bonds, right? And then here's the unsaturated fatty acid. There's a double bond, there's a double bond. So it leaves us some space in here. So that molecule's got some flexibility to it, so it's a liquid at room temperature. Sometimes you'll hear the term trans fat. The term trans and cis designate the position of a hydrogen atom around that double bond. Notice here that on that double bond, our hydrogens are all on the same side of that bond. So that's a cis fat. Trans fat is where they're on opposite sides. We really don't see trans fats in nature, but we made them because plant oils are cheap, but they don't last very long. Animal fats are more expensive to make, but they last forever. So we get sort of a blend. We get this semi-solid fat that's great and tasty in baking. That's the trans fat. They invented this in the early 1900s. We allowed hydrogen atoms to react with the oil. We disrupted that bond. We created a partially hydrogenated oil. That term, partially hydrogenated, means trans fat. First major sales of this was as Crisco, partially hydrogenated cottonseed oil. Thing is, trans fats suck. They don't occur in nature. We've banned them. In the original sort of thing, New York City and California were the first to ban trans fats. Now the FDA has banned trans fats across the board. All right, so what do fats do? Well, they're fat, so their energy storage, their insulation. The phospholipid is a fat. It's what all your cell membranes are made out of. It looks like this. More on that later. The phospholipid is amphipathic. It's both hydrophobic and hydrophilic. Again, more on that later. There's all these phospholipids. Steroids are lipids. These are chemical signals. All steroids are made from this molecule. That's cholesterol. Cholesterol is something that's essential for life because steroids are made out of it. And it's in all your cell membranes. It keeps them stable. There are 4 different vitamins that are fat soluble: A, D, E, and K. So those are lipids. The eicosanoids are lipids. These are chemical signals between cells. They're involved in inflammation and blood clotting and labor contractions. So lots more function for lipid than we saw for carbohydrate. Now, as big a difference as that was, there's a lot more difference between that and proteins. Proteins are polymers of amino acids. There's 20 different amino acids. They're all different. They're combined in different ways in these big proteins. What do proteins do? Freaking everything. Functions of proteins, everything is a function of proteins. Everything. That giant Jurassic Park list of all the letters in DNA. DNA is a giant blueprint for making proteins. Our genetic code is nothing but instructions on how to make proteins. It is everything. All right, so in a protein, we sort of break this down into levels of structure. The primary structure is that arrangement of amino acids determined by DNA. So you get that big Jurassic Park screen of letters, and you decode that, and you write down the order of amino acids. Just write it down. That's the primary structure. But proteins aren't just these big chains. What's going to happen is these groups are going to push and pull on each other. We're going to form some hydrogen bonds. Remember that slight attraction between polar molecules. And that's going to cause this thing to fold or twist. That gives us our secondary structure. Would there be an alpha helix, which is this fun corkscrew, or a beta sheet, which is that zigzag? Then we come to the tertiary structure. This is the three-dimensional shape of the protein. This is the important thing, because shape of a protein determines its function. How important is this? A great example of this is in a big protein called hemoglobin. Now, hemoglobin is a protein in your red blood cells that's going to bind to oxygen and allow those red blood cells to carry oxygen through your bloodstream. Now, it is a very, very big protein. If we go back to that primary structure and we swap one amino acid in hemoglobin, then we change the way the secondary and the tertiary structure comes out. So normal hemoglobin, the abbreviation for hemoglobin is this. Change that one amino acid and we get this. HBS is sickle cell hemoglobin. And what happens is your red blood cells go from being these little sphere things to looking like this. Doesn't carry oxygen as well, makes the blood cells weird shaped. It's problematic because blood tends to clump together and it sucks at carrying oxygen. So the shape is essential to function. All proteins have primary, secondary, tertiary structure. There are a few that have what's called a quaternary structure. Then we get more than one polypeptides linked together, and hemoglobin is one of these. They're physically chained together. Here you have the quaternary structure of an albumin thing where they're stuck together in the end. Breaking a protein is called denaturation. Enough pH change, enough heat will break a protein. It changes the shape of the protein. It breaks that tertiary structure. Often it's permanent. When you fry an egg, or cook an egg anyway, when the egg white goes from being translucent to being white, you're denaturing proteins in the egg, but with heat. And that's a permanent change. Conjugated proteins have something else incorporated in them. Enzyme we talked about, biological catalysts. Enzymes usually used in an ASE. There's another example of an enzyme working. Well, then we come to nucleic acids. Nucleic acids, big giant molecules. This is genetic stuff. I'm going to ask you about the base pairs here. I'm going to ask you to pair them up. RNA, DNA, this is all genetic stuff. We'll talk about what's going on. ATP is going to be important. ATP, this is our energy currency. We'll talk about how that works later. But it is the energy. The function of ATP is it is our energy molecule. And there's ATP doing stuff. All right, again, don't spend a lot of time here. Brief overview of chemistry, just to put us on the same page. You're not going to have any direct chemistry questions. All I'm looking for is this short idea of how this works. Next lecture, cells more important.